Well, welcome everybody. I'm Bill Fry with the Social Science Data Analysis Network at the University of Michigan. And what we've sponsored over the course of this last month are 3 extensive webinars under the title Analyzing the 2020 Census and the 2016 to 2020 ACS data using R, a webinar series for teachers and researchers. And we're very pleased to have this have with us is Kyle Walker, who's been presenting all of this material. He's a professor of geography at Texas Christian University, but even more importantly, he's a renowned expert on analyzing census data and census data products with R. And he is the author of the book, Analyzing US Census Data, Methods, Maps, and Models in R. We're pleased to have him here today to talk about using the 2016-2020 ACS estimates in R. If you follow things pretty closely, you'll know that these numbers just came out a week ago yesterday to the public. So this is really a quick turnaround to be able to have the ability to access these very new census products with R. And I know Kyle has worked hard to make this available to everyone. We're pleased to have you here today. You'll be able to sort of chat and ask questions, and we'll be able to answer those questions. But before we turn it over to Kyle, I'm going to turn it over to John J.P. DeWitt, also with the SSDan project, for a few opening ground rules.
Hi, everyone. So as Bill mentioned, this is the third in our third episode in our webinar series this month. The link that I earlier provided in the chat has links to the recordings and to some of the materials that we'll use today. The session will proceed in large part in sort of 3 50-minute blocks. So we'll have a couple opportunities for breaks where we can get up, stretch our legs, maybe get a glass of water. But also during that time, as Kyle will explain, he'll provide some exercises. But it's also a great time to ask some questions. So when we come back from break, Kyle will answer some of the questions that you've posed. So please go ahead and use the Q&A feature in Zoom to pose those questions to us so we can ask Kyle those questions after the breaks. Also, if you have other issues that may come up or other questions, please also feel free to use the chat. And if you are able to answer some of the questions that might be posed, if you feel confident in answering some of those questions, we enjoy the great community that we have here attending the webinar. We found that many people are experts and have experienced similar problems. So feel free, if you have experienced the same issue and can answer a question, please go ahead. But I know that you are all here to listen to Kyle. And so without further ado, I'll turn things over to him to get things started.
All right, well, thank you so much for everyone in attendance. Thank you to JP and Bill for the generous introductions. And I'm gonna go ahead and share my screen and get started. So we're gonna move here. All right. So as we've discussed, today is the third in our 3 workshop series that we've been doing this month on new census data and how you use it using the R programming language and software environment. And today is all about using the new 2016 to 2020 5-year ACS, or American Community Survey estimates, in R. And this is kind of fun to be able to do this because these estimates that usually come out in December, early December of every year, but due to the COVID-19 pandemic and significant data collection issues in the 2020 ACS, which I'll cover in some detail later in the presentation, the release of these estimates were delayed because Census wanted to be confident that they were producing estimates that we could rely on. And after they achieved this level of confidence, they said, we're going to release it in March. And they did. And the timing was such that they came out on March 17th, and they work in R. You can get them now. And I'm going to show you how to get the freshest data and do some interesting visualizations and analytics with them. So to get started, let's talk through a little bit. Again, JP and Bill, much appreciated the introduction. Just to reiterate, I'm an associate professor of geography at TCU, but I also work extensively as a spatial data science consultant on a variety of different projects across industries. And I, even help individuals with our training needs or tidycensus training needs quite frequently. So if any of you are looking for help in those areas, please drop me a note. Be happy to chat. I have been investing heavily, my professional time into developing out tools for working with census data over the past few years. And so tidycensus and tidyverse are packages that I've developed to work specifically with census data. I have a few other kind of lesser known packages. Mapbox API is one of my favorites. It gives you access to Mapbox navigation and map and web mapping services. It might be one that's worth checking out. My book is coming out, hopefully in print toward the end of the year. What I'm doing right now is you can access my book from the link here, Analyzing US Census Data, Methods, Maps, and Models in R. I'm updating everything over the next 2 weeks to the new data so that it is as up to date as possible using 2016 to 2020 ACS estimates. So you can read through it right now. It's going to be freshly updated and then sent off to the publisher probably in April. So take a look at that. A few other things. Slides are up for the March 10th and last week's workshops, and so we're covering ACS data today. And so what we're going to be doing is dividing up the workshop into 3 chunks, and we'll generally go about 50 minutes per chunk and then take a short break so you can stretch your legs, so I can stretch my legs. And I've organized them generally into 3 components. So in the first hour, we're going to be focusing on an overview of the new 2016 to 2020 5-year ACS estimates. What are they? How do you use them? How do you access them in R? How do you interpret them? And then in the second hour, we're going to focus exclusively on data visualization, basically be walking through kind of 3 specific use cases and talking you through how to set up everything from sort of more basic visualizations to more complex ones. And so it'll be drawing on, for those of you who have made it to all 3 of the webinars, some of the skills that we've learned in the past 2 sessions, but also there should be content for those of you who are just joining us for the first time today, content for you to still get up and running. In hour 3, we're going to cover some more advanced topics that are germane to the 2020 ACS data specifically. And so one is going to be margins of error. So the 2016 to 2020 ACS is distinctive in that it incorporates information that happened during the COVID-19 pandemic, and especially when there was a lot of uncertainty involved in 2020. This means that there were issues with the 2020 ACS that haven't affected the survey in previous years to the same degree. And so that gets baked into your estimates. And so we're going to talk about what's going on there, how to handle margins of error in the ACS. And then the other piece that's important is frequently analysts are tasked with analyzing demographic change over time. This is straightforward, say at the state or county level, usually because state boundaries rarely change, county boundaries almost never change, though they do sometimes. But smaller geographies like census tracts and block groups change with every decennial census. And so the 2016 to 2020 ACS is the first 5-year ACS data set to use 2020 census boundaries instead of 2010 boundaries. And so this introduces potential issues for time series analysis for small areas. And we'll talk about some strategies for handling that toward the end. Let's talk a little bit about general setup. So I'm mentioning links. You might be wondering how you get access to the slides. JP provided some links for you. The quickest way to get booted up, I think, with some links available is to jump over to my GitHub page. And so if you're not familiar with GitHub is a hosting service for developers to host their code and all sorts of other stuff. My book is hosted on GitHub's website. So if you search for me, Walker KE. And if you search specifically for UMich-workshop-2022 in GitHub, you'll find this page. And so this page has all of the code and all of the links that you'll need to get up and running. And so there are a couple different ways to get started. If you want to follow along with the slides and have those up on your computer, they're linked here in the README. You can just click and it'll pop up. If you are an advanced R user or an experience or just someone who already has R installed on their machine, there are two ways that you can get up and running with the code for today. One way is if you're familiar with Git and GitHub, you can clone the repository to your computer. So open up a terminal, change to an appropriate directory where you want to store all this information, and then use this command in your terminal to clone the repository to your computer, and then go ahead and open up the project in RStudio. If you're experienced with R but less experienced with Git, you can find this folder that says ACS data, and you can go in the code.r script. This is all our code that we're using today. So you can just go in and you can actually just copy paste all of this into an R script if you want to. Alternatively, you can download the entire workshop materials if you want to by clicking the green code button and then choosing download zip. And that will download all the materials to your computer. If you're less experienced with R, if you haven't used it before, or if you are unfamiliar with RStudio, you can use the pre-built RStudio Cloud environment. RStudio Cloud is a cloud service provided by RStudio to run R without needing to install R on your computer. And so if you click this link, as I'll do here, you'll notice that RStudio Cloud will pop up, and you can either sign up for an account by clicking this tab. All you need is an email and a password, first and last name, or you can sign up with an existing Google or GitHub account if you have one. I'm going to illustrate how to get this started. I'll click Login with Google. I'll choose a Google account. And what this will do is build a temporary version of the project in RStudio Cloud for me to work on. It'll just take a few moments to deploy the project, but one great thing about using RStudio Cloud is all of the packages, the R packages we'll be using today are pre-installed. So there's some other stuff that's coming through here that you'll want to clean up. So follow these steps in RStudio Cloud to get started. Look for the little broom icon right here in the upper right of your console, and click there to clear the console. And then look for the colored in broom icon here in your environment tab and click clear objects from the workspace, and then choose yes. After that, what you can do is customize your workspace a little bit. What I am going to have set up is I'm going to click this little window icon and choose console on right, because I like to have my R console on the right. And this will set up a layout where you have an R script editor on the left-hand side, the R console where you can type in interactive commands on the right-hand side, your environment pane, which is going to show all of the objects that you create over the course of the workshop on the bottom left, and then your files browser and your plot viewer on the bottom right. What you'll do to get the materials up and running for this workshop is you'll click the ACS data folder, and then you'll click the code.r script. What that will pull up is an R script that you can use to run. If you've never used R before, the way that you run code in a script is you can highlight it, and you'll notice it highlights as blue, and you'll click the run button, or you can use the keyboard shortcut Control-Enter to run that code. So basically, what I'm doing here is I'll load in the tidycensus package, and then I'll set my census API key using an API key that I've provided for you. If I run that, that brings in all of the functions in tidycensus to get ACS data and make them available to me, and it authenticates my API key, which I'll explain in brief detail for those of you who are new in just a moment. So one caveat, our Studio Cloud, I should say two things. First thing is right now we're running a temporary copy of the project. What you're going to want to do is click Save a Permanent Copy to copy that project over to your account, and that'll store it in your account. The caveat with using our Studio Cloud is it is a free service, which is wonderful, but understandably, because our studio wants you to pay for it if you're using it for heavy duty computing, a free service means limited features, and you only get 1 GB of memory, which for some of the examples we're going to be running today is not enough. For most of the examples, it's fine, but when we want to cover some more advanced workflows, this is when potentially you're going to want to get up and running again. So or move that over to your own computer, set up R&R Studio. And if for some reason, if you're coming from a previous workshop and you don't see the ACS data folder, it is entirely possible that the workspace will need to be refreshed. You can potentially go and grab that code from GitHub, or basically create a new project. When you bring this over, you could potentially create a new project and get access to the new code. But that's all going to be on GitHub for you. If you need to, you can always create a new R script, clicking the little drop-down menu here, click R script, that'll create a new R script, and then you can copy any code over from GitHub that you need. So because of the memory limitation issues of our Studio Cloud, I'm not going to be working in our Studio Cloud today. I'm going to be working on my own local version of R. And so I'll be flipping back and forth between basically the slides and my own version of R, which you can see here, which has the same layout, though I have a dark mode. If you want to change the layout of your R Studio, you can click Tools, Global Options, and then Appearance, and you can choose a different editor theme. So mine has a dark layout, but it has the same organization here. So that's what we need to get started. And let's go ahead and keep moving. If you are running R locally and you want to run every example, I've actually added some new features to tidycensus this week to deal with some of the new data. Most of the examples will work. I'll let you know when they won't. But if you want the most up-to-date version of tidycensus to get everything to run, use this code here. Install.packages remotes, and then remotes : install GitHub Walker KE tidycensus. This brings in the latest version of tidycensus to your computer, including edits that I have made a couple days ago to add new features that you can use. So I'm excited to show some of these new features. You'll be some of the first to see them. All right, so let's start digging in with some examples. With part one, this is an overview of 2016 to 2020 ACS data in our tidycensus. And so let's give a little bit of background about the ACS. What is it exactly? We're familiar with decennial census data. What is the ACS? Well, if you rewind all the way back to Census 2000, we used to have two surveys sent out to the US population. You would have the census short form, which had core demographic questions like age and race. And then that was sent to everybody. And then you had the census long form, which was sent out to about 1 in 6 households that included all other demographic questions, income, education, and the like. Since then, in the 2010 decennial census, we no longer use the long form, and instead we use the American Community Survey to get that richer set of demographic estimates. And so the ACS is an annual survey, and it's sent out on a rolling basis throughout a year by the US Census Bureau to around 3.5 million US households per year. And so that'll cover maybe 10 to 12 million people who will be accounted for in the ACS. And so the ACS, as I mentioned, it covers topics that you don't get in the decennial US Census, which are of acute interest to really just about anybody working with demographic data. So you can get income information, education, language, and more detailed housing characteristics, among other things. The ACS comes in two flavors. One is the one-year estimates, which are released only for geographies of population 65,000 and up. And so you get more up-to-date data, but for small geographies, you don't get data at all. For those smaller geographies, all the way down to the census block group, we use the 5-year ACS estimates, which are basically averaged over a 5-year period. The most recent is 2016 to 2020, so it's bringing in information from 2016 to 2020 to generate a more robust sample with which we can kind of infer characteristics of the US population. One caveat about the one-year data, because of data collection issues that occurred during the COVID-19 pandemic, basically the 2020 ACS, they only got about 2/3 of surveys back as compared to previous years. And so the Census Bureau decided not to release the 2021 year ACS, and instead they released it as a series of experimental estimates that are only available for data download from the census website. ACS data, as they're based on a survey and a sample of the US population, the data are delivered as estimates rather than true counts. And those estimates are characterized by a margin of error, which allows us to quantify uncertainty around those estimates. And we'll spend a fair amount of time talking about how to handle that uncertainty as we move forward in this workshop. We're going to be using the tidycensus R package today, which if you've attended the previous two workshops, you have an existing familiarity with. If you're new, then you will be introduced to this package today. The tidycensus R package is a package that I first developed 5 years ago to access a variety of different Census Bureau data sets. It doesn't access all of them. You'll want the Census API R package for that, but it accesses some of the most popular ones. So the Decennial US Census, American Community Survey, Population Estimates Program, the Migration Flows API, I don't have that up there, but also the Public Use Microdata Series APIs. And what I really like about tidycensus, and the reason why I wrote it, is I wanted to resolve some of the time I was spending going through various menus on the census website, pulling data down, wrangling that data, getting it merged to census geometries for mapping. Tidycensus does all of this for you. It pulls down requested data from the census website, from its application programming interface or API, and then wrangles that data internally to give you back data that is basically ready to go for use with the popular tidyverse suite of packages for data wrangling. Additionally, for geospatial analysts, you can automatically merge census geometries to data for mapping. We spent the entire workshop covering this last week, but we are going to touch on it again briefly here to discuss how to work with spatial data in the ACS. It also has a few other features to make it easier to work with microdata, to work with margins of error. And one of my favorite features, one of my main motivations for writing it, I could never remember zip codes for locations that I wanted. You can just type in the state or county names instead. So let's talk a little bit about using tidycensus, and I want to preface with a little bit about framing. So this is the third of a 3-workshop series in which we have already spent 6 hours covering extensively how to work with R, how to use tidycensus, and how to map data and visualize data in R. So I see, some of you have attended those workshops previously. So I'm not going to repeat everything, I don't have time to, that I covered in those workshops, but some of you also are new and you haven't attended the previous 2. And so I'm trying to kind of take a middle ground here with respect to the learning curve in the content. I'm going to provide a gentle introduction to each section, and then we're going to go a little bit quicker through the content and move more toward advanced examples a little faster than we might have in the first 2 workshops. So hopefully there'll be something there for beginners, and there'll be something there for experienced users as well. So in tidycensus, we use the get ACS function to allow us to access ACS data. You can get ACS data for 2005 through 2020. And so we're focusing today on the 2016 to 2020 ACS estimates. So you'll supply the argument year equals 20 to get ACS. In the next released version of tidycensus, when I ship it off to CRAN with all the new updates, this will be the default year in get ACS. I have not made that change yet. So if you don't supply a year, it will still default to the old 2015 to 2019 ACS estimates. When a new release comes out, that's probably coming next month, I would think, we're going to move that default year to 2020. For now, you need to specify year equals 2020 to get the new data. The other required arguments include geography, which specify the level of aggregation for our data, and variables, which is one or more ACS variable IDs specifying the data we want to get. I'll explain how to do that in just a moment. Get ACS defaults to the 5-year American Community Survey with the argument survey equals ACS 5. You can put in survey equals ACS 1, but if you try to do that with the year equals 2020, it will throw an error because tidycensus does not support the 1-year 2020 ACS experimental estimates. They aren't published to the API. They're in a different format from previous years. And so tidycensus doesn't support those estimates. You need to download those manually. So as a review, to use tidycensus, you need the tidycensus package installed. If you're using RStudio Cloud, it's pre-installed along with its dependencies. You'll also need to authenticate with an API key. If you've been to these workshops before, you've already done that. Otherwise, that code is available in RStudio Cloud for you to run. So what I'm going to do is I'm going to hop over here to RStudio, and I'm going to get that set up. I don't need to put in Census API key because I already have my Census API key installed. So I'm just going to run library tidycensus. I bring in tidycensus, and I am good to go. So let's get started trying out how to use get ACS for the 2016 to 2020 ACS estimates. So we load in the tidycensus library. And then we run the function using arguments and assignment. And so in R, the assignment operator is this arrow sign, which is your greater than and then M dash. And so if you type get ACS, but the first thing that you'll do is you'll specify an object name to which you can assign an object. And so just one brief comment that I see in the chat, what I'm going to do real quick, if you have a locally installed version of R, I'm going to jump over real quick back to RStudio Cloud, just to make sure that everybody gets up and running okay. I'm going to boot this up. I'm going to give you an API key that you all can use if you don't have your own. So I just posted an API key in the chat. Sorry, it only went to the hosts. Okay, that's an API key that you can use. I would recommend that you get your own, but that's one that you can use for the purposes of today. All right, so what we're doing is we're naming an object called Born in Mexico, and we're assigning to it using R's assignment operator the result of the function get ACS for state level geography for a specific variable ID. That means the number of people living in that state that were born in Mexico. And we're grabbing data from the 2020 ACS. And so year equals 2020 for the 5-year ACS refers to the end year. So it's the end year of the 5-year period. So year equals 2020 is 2016 to 2020 data. Year equals 2019 is 2015 to 2019, and so on and so forth. So let's try running this code. I run Born in Mexico. I pull down data from the ACS, I get it instantaneously, and then I can take a peek at my data and see what I got back. So it looks like I got a data set that has 52 rows and 5 columns. And so what we see here is the general structure of a data set that returns data from the ACS. And so the estimate column here, you can see, has the estimated number of people born in Mexico, living in Alabama, living in Alaska, living in Arizona, and so on and so forth. There's just another illustration of that output. You can also grab from the ACS, you can grab estimated counts, and you can also grab estimated derived information. So here is the code for median age by state. And we're creating a new object called median age. And we'll get a result that looks like this. So I'm going to jump back over to R and show you how quickly it is to get data instantaneously for really any ACS variable that you want. And so you can see some of these differences. Alaska, very young, Florida, quite a bit older. So what exactly are we looking at here? Jumping back to the slides real quick. ACS data by default are returned with 5 columns. So you'll see 5 columns over here: GeoID, name, variable, estimate, and MOE. So what do those different columns mean? GeoID is going to be a unique identifier for a census geographic unit. And so what that is, it's basically a tessellation of FIPS codes, if you will, for each unit. And so I'll talk a little bit more about how that plays out when we get to smaller geographies. But for states, it's going to be your 2-digit FIPS code, so Federal Information Processing Standard code. The name column is going to be a descriptive name for the geographic unit. And so, I mean, if you're a census wonk, you'll know that Alabama's FIPS code is 01. And but we don't necessarily associate Alabama with 01. And so the name column gives us a more descriptive set of information about that geography. Variable refers to the ACS variable ID that you requested. And then you have estimate and MOE. So for those of you who attended previous sessions on the 2020 census, we just get back a value column. You don't get estimate and MOE, but because ACS data are estimates characterized by a margin of error, the estimate column gives you the ACS estimate, and it's important to interpret these as characteristics rather than true counts, because each estimate is characterized by uncertainty around it that is represented quantitatively with the MOE. And so the MOE, or margin of error, is that margin of error associated with the estimate at a 90% confidence level. And so if you go back to your data here, what we see is the ACS estimate for 2016 to 2020 of the Mexican-born population in Alabama is 46,927. The margin of error is 1,846, which means we're 90% sure that the true value of the Mexican-born population in Alabama is either about 1,800 fewer or 1,800 more than this estimate. So it's a way of representing uncertainty in the data. And we'll talk about how to use that to make comparisons a little bit later. If you prefer to have all this information spread across the columns, using the argument output equals wide will basically do just that. And I'll show you briefly what this looks like interactively. Say if we wanted median age, but we wanted it in wide form instead of long form, which is the default returned by tidycensus, I could add the argument here, output equals wide. And if I do that, take a look at my screen and see what it looks like now, and then note how it changes. Output equals wide is structured differently. There's no longer an estimate in an MOE column, but rather the column names are the variable IDs. And here we have the suffix E meaning estimate, and the suffix M meaning margin of error. And so if you were to ask for multiple variables in one call, those will be all spread across the columns instead of stacked in the rows. So let's talk a little bit about geography, and let's talk a little bit about variables in the ACS as we get more comfortable working with this information. So we use the geography argument in getACS to access data that's aggregated to varying levels of the census hierarchy. And if you follow the link here and you look at chapter 2 of the Analyzing US Census Data book, and so, Eric, I noticed you just asked, is it possible to pull MOEs in wide form? That's exactly what we just did. So you see here, the columns that have a suffix with M, that's your margin of error. And so if I were asking for multiple variables, let me show you just briefly how to do that. If I use the C function, which is for combine, and I ask for multiple variables, like let's say we're asking for median age and then total population, which is 01, 003, 001. And I run that, you'll notice here that all of those are spread across the columns. So here I have margin of error corresponding to this estimate, and total population for states is controlled. So that doesn't have an associated margin of error. But if it did, that would show. So with respect to geography, remember that ACS data start at the block group level. So census blocks are the smallest geography at which we can get data in the decennial census data. We can't get block level data for the ACS. We start at the block group. You can get ACS data for all of these other geographies. And what we can do is grab data as specified at the link here. So if you follow the link in the slides here to my book, I'm going to just jump over real quick. You'll get a table that shows you the geography and how to specify it, and in what data sets it's available. Not all geographies are available in all data sets. So you kind of have to get a feel for it a little bit, how it works. But there are a lot of geographies that you can get. When you're asking for geographies, you'll notice in the census API, sometimes the geographies are formatted in a very verbose way. So one of the most popular geographies to get is going to be your metro area, which is in the API, metropolitan statistical area / micropolitan statistical area, which is a lot to type. So we refer to these in the census as core-based statistical areas, or CBSAs. And so I alias that in tidycensus, where you can just type in geography equals CBSA instead of having to type out that entire long string. Now, granted, you can type that out, that long string, if you want to. Both will work. I do the same thing for zip code tabulation areas, which are basically shapes that represent roughly the extent of zip codes, USPS zip codes. And so you can type in ZICTA, ZCTA, to alias for zip code tabulation area if you want zips as well. So just to show you briefly how this works, I can type in geography equals CBSA if I want to get back information for all of the metro and micro areas in the US. I'm going to hop back over here to our studio, run that code. And here we have information on all of those metro and micro areas in the US with their corresponding ACS estimates. We can also grab geographic subsets using state and county arguments. And so with respect to geographic subsets, oftentimes, say for block groups, you're going to need to or want to get smaller subsets. And so in this case, we're going to grab median age data for block groups in Washtenaw County. And so I specify the geography equals block group. I specify the appropriate variable for median age, but I also can say, give me back for the state of Michigan. I can use either the word Michigan, or I can use the postal abbreviation for Michigan. Or if I know the FIPS code, I can use that too. And then county, I can put in Washtenaw. I put in year equals 2020, and that subsets it down to Washtenaw County and gives me estimates and margins of error. So let's go back to our studio and let's take a look at how that works. So here I get data back instantaneously for all 308 block groups in Washtenaw County, along with their median age estimate and margin of error. You'll notice for block groups, sometimes you'll get back NAs, which is R's notation for missing data. Those NAs mean that we simply don't have an estimate, or there are too few people to derive an estimate in that particular location, which when you're getting down to small geographies, like the census tract or the block group, you'll start to see that a little bit more commonly. For example, local to me in Dallas-Fort Worth, nobody lives in the airport. And so you'll get back NAs for demographic statistics for those block groups that cover the DFW airport. So moving through these examples, and if we go back here to the slides, I want to spend a little bit of time talking about available variables and data sets in the 5-year ACS. So we have access to the ACS detailed tables, which is your kind of core demographic data set. That is all of the different ACS variables. There are around 28,000 in the 2016 to 2020 ACS. If you want pre-computed data that for common variables, take a look at the data profile or the subject tables. Those are pretty great because they give you pre-computed percentages for many interesting statistics that use appropriate denominators, or they use coarser age bands for, say, ages, which is sometimes kind of nice. So then they're much easier to browse. So take a look at those. If you are using the GitHub version of tidycensus, I just this week published support for the ACS comparison profile, which allows you to grab data simultaneously for 2016 to 2020 and the previous 5-year period, 2011 to 2015, to make appropriate comparisons and do time series analysis. I will show you how to do this a little bit later. So another brand new feature that's just in tidycensus, that is just in the GitHub version of tidycensus, tells you in the detailed tables the smallest geography at which data are available. And so I want to show you briefly how this works. I'm going to jump back over to our studio here. And I mentioned the load variables function. I don't have that in the script, so I'm going to show you how to type this in interactively. If I want to get all of the information for all of the variables available in the 2016 to 2020 ACS, I can type in something like ACS vars, and I assign to it the result of load variables. I specify a year of 2020, and then a data set of ACS 5. I run that code, and even though it's 28,000 some variables, it only takes a few moments to pull down. And then a little trick as well, and this one I find pretty fun. There is an interactive data browser in our studio, and if you hold the control key and click on any object that exists, like ACS vars, it'll pop it open in your variables viewer, which is pretty cool. Or alternatively, is use the view command. So I can type in view ACS_vars, and that'll pop open this interactive viewer. And so you have 4 columns for the detailed tables. You have the name, which is going to be the variable ID that you'll use to get data. You'll have a label, which tells you what the content of that variable is. You'll have a concept, which is the general category. And if you scroll to the right here, make this a little smaller, it actually shows you the smallest geography at which the data are available. So you can see that some variables are available at the block group level, But if we scroll down, there are other variables that are just available at the census tract level. And so if you try to pull any of these variables at the block group level, you'll get all NAs. The call will work, but you won't get data back. And so this is a brand new update only in the GitHub version that gives you this extra information. I was pretty excited to bring that in. All right, so let's spend a few moments. It will probably go all the way up until 11 o'clock before breaking, because we spent a fair amount of time doing setup, and then we'll break after that. And so let's spend some time talking about analyzing 2016 to 2020 ACS data. And so if you attended the first workshop, you'll remember that we covered a variety of methods for analyzing census data using tidyverse tools. And so the tidyverse is a suite of packages developed by our studio that are optimized to work together to accomplish a variety of common data wrangling tasks. I want to show you briefly how you can use some of those tools to answer some interesting questions. And so we're going to grab a data set for all counties in the United States of median home value in the 2016 to 2020 ACS. And so your variable that you're going to use here, which you could have searched for in that variables table, is B25077_001. So let's go ahead and pull that information down. And I mentioned in the slides, the quickest way to start just analyzing your data is to pop up the object using view in your variables browser. And so this is median home value as an interactive table. And I can go through and I can filter my data if I want to. I can use this search box to search for specific locations. Importantly, I can also sort my data in descending and ascending order. So what are the most affordable counties in the entire US? Well, King County, Texas has the lowest median home value in the entire country at $22,800. You have a couple others in South Dakota, a few others in Texas, very small counties in rural Texas. You can see these are going to be your most affordable, or kind of the lowest median home value counties in the US. If you click again to sort in descending order, you'll see the most expensive counties in the US. And unsurprisingly, they tend to be in the area. So San Mateo County clocks in at number 1 at about $1.16 million as its median home value. So with San Francisco County, so the city of San Francisco, just right in as second place. And so this is one way that we can browse and analyze our data, but there are other ways to use formal tools to do this as well. And so let's go ahead and ask a question here. Which counties are in the top 10% nationally for median home values? And then how does this break down by state? We're going to set up an analytic workflow to answer that question using the data that we've acquired with tidycensus and using tidyverse data wrangling tools. So our first step is we're going to extract those top 10% of values from our data set. And the tidyverse sets up really well to give us tools that make this straightforward. I'm going to talk you through, as we run this code, exactly what it's doing. Our output is going to grab us something that looks like this, that gives us the top 10% of counties by median home value. So if we go back here to our studio, a little bit of background about tidyverse data wrangling. We're creating a new object named top 10% that uses tidyverse tools to modify that object that is coming in, which is median home value. We use the pipe operator, which is percentage sign, kind of less than percentage sign. And what that pipe operator does, you can read it as the word then. And so we're saying here, median home value, we're creating a new data set named top 10%, where we take the median home value data set, then we mutate it to add a new column named percentile, which is equal to the percentile rank of the estimate column, which is storing our median home values. Then we filter that data set for only those rows, and you can interpret this kind of like a SQL query, where only those rows where the percentile value is greater than or equal to 2.9. We can run this code through, and we get back a data set that contains the top 10% of counties by median home value. You can see that several of those are in Alaska. You can see some of them are in Arizona. You could open up that data set in the interactive browser and file browser, and you could take a look at that too. So that basically answers question one. Which counties are in the top 10% for median income? Again, we could control click and take a look at it. And so we can see a lot of California counties, a lot of Colorado counties in there. But we're interested in sort of the second question too. How does this break down by state? Can I summarize this by state? Well, you'll notice there isn't a state column in the data set. There's a name, but the name itself has state information embedded in it. So we can use additional tidyverse tools to separate this column at a delimiter, which in this case is a comma space, and create new columns. So thinking about how we do this, going back to the slides, what separate can do is find a separator in a column and split that column into different columns. We're basically saying take our name column here, separate it at comma space, and then separate it into where the first column should be county and the second column should be state. If we run that code through, we actually then get a county name column and a state column, which allows us to do analytics by state. The next piece then is we want to analyze that information by state. And we're going to use a group by and summarize workflow. And so this will be familiar to those of you who attended the first workshop. If you're less familiar, what group by does is it identifies unique values in a given column and splits the data set into groups based on those values. It then applies a function to any function that is called to each of those groups. And in this case, what summarize does is it applies a function to each group and returns a data set that combines those group-wise tabulations back together. The last method I'm using from the tidyverse here is arrange, where I'm arranging the data set now in descending order of this new n column, which is calculated from the n function. And the n function just gives you the number of rows. And so in this particular case, the result I'll get back will look like this. That'll be my state summary. So let's run that in R. So first things first, I separate my data set into state and county columns. And you can see here, now I have a county and a state column. And next, I summarize my data. I group by values in the state column. I tabulate the number of rows in each group. And then I print out the result in descending order. You can see California comes in at number 1 with 43 counties in the top 10% for home values. Virginia, number 2, Colorado 3, Oregon 4, and Washington 5. So West Coast, high home values in the West Coast are definitely influencing this data set. All right, so that concludes part 1. I have a few exercises for you. So we're going to take, I would say, around a 10-minute break or so. Maybe we could reconvene JP right around 5 minutes after the hour so we keep things moving. So let's take around a 7-minute break or so. And you can try out these exercises if you want to. First, use load variables to browse the available variables in the ACS, just like I showed you how to do. Find a variable that interests you and then try reproducing one of the examples in this section with that variable. And then the second exercise, if you want to get to it, is use those tidyverse functions covered in this section and explore that variable for all counties in the US. So basically reproduce the workflow that we did for median home values and do it for a different variable. So which counties have the largest estimate and which have the smallest. So let's take a few moments to do that. Let's come back at about 5 after the hour. Just briefly, without delving into a specific question, there's a lot of, there's maybe two questions that I want to answer real quick. One is margins of error, derived margins of error. Hour 3 is really focusing on margins of error. So we're going to cover all of that in a little bit. So just stay tuned for hour 3. You'll get most of those margin of error questions answered. There's another really good question though about finding the right variables. This is something that is honestly it is challenging, and so there's a couple resources that you might be interested in taking a look at. One is Census Reporter. That's what I tend to use. Census Reporter is a project out of the Night Lab at Northwestern University that allows for kind of interactive browsing of ACS variables. It's really, really good for finding variables. There's another commercial product that is called Social Explorer that is pretty great for that. And it's interesting, there's a new R package that just came out from a grad student at Harvard who's been sort of heavily involved in redistricting work that kind of wrote a light wrapper to tidycensus called Easy Census that has some sort of advanced variable searching functionality. I haven't personally tried it yet, but it looks pretty promising for finding interesting variables. So that might be something that's worth checking out as well. But Census Reporter is where I really turn to. Load variables does it gets you part of the way there, but still combing through 28,000 variables is pretty hard. So Census Reporter tends to be my preferred resource. Let's go ahead and keep moving through, and we're going to talk about data visualization. So if you attended the previous 2 workshops, we covered a fairly wide range of methods for visualizing census data. We spent a whole hour in the first workshop focusing on data visualization methods and techniques for 2020 decennial data. And then the second workshop was largely all about cartography. We learned about spatial data. We learned about how to make maps, focusing on the TMap R package. And we learned how to make a few interactive maps as well. And so if you didn't get an opportunity, take a look at the slides for that. And the code is in the repository as well. You can go ahead and try it out and run it. So what this portion of the workshop is, it's a repackaging of some of that content from previous workshops, but showing some tailored examples to the ACS, because the decennial data, and this is a challenge I ran into in preparing the visualization examples for the decennial data, especially the decennial data that we have. So for 2020, pretty much all we have for decennial US Census data is total population, race, ethnicity, and group quarter status. And that is basically it. We also have occupied and vacant households. And so there really aren't a lot of options available for data visualization. When we have the ACS, we have all of the variables, and that gives us a lot of information that we can potentially visualize. And so we're going to delve into this a little bit more, create some creative plots, and think about some advanced use cases and examples in addition to some basic examples. So let's go ahead and get started. We're going to be focusing on using ggplot2, which is the most popular data visualization package in R. It's probably one of the top 5 most popular R packages, period. And this originally was developed by Hadley Wickham, chief scientist at RStudio, to implement a layered grammar of graphics approach to data visualization in R. And so the way that you create plots in ggplot2 is you typically start with the ggplot function, which initializes your chart. You then supply a data set and then an aesthetic mapping using the AES function. And the aesthetic mapping maps characteristics of your data to different chart elements. So you can map a column to the x-axis or a column to the y-axis, or you can map a column to the color of chart elements. It's almost infinitely customizable, and it's there's a reason why it's one of the most popular R packages there is. You then layer on additional elements. So once you specify an aesthetic mapping, you tell ggplot2 how to draw shapes on your plot using a geom, short for sort of geometric object function. And then you can style your plot accordingly. And so here I have a very basic example that shows how to use the tidyverse, and we're using the scales package, which comes pre-installed with the tidyverse, to create a plot where our data object is median home value. Our aesthetic mapping is mapping those median home values in the estimate column to the x-axis. We then draw a histogram using geom histogram. We're setting the number of bins for the histogram to 30. And then we use scale x continuous to modify the underlying scale at which the ticks are reported. So I use the label dollar function from the scales package to change the labels from the default numbers to something that looks more like money. And so trying this out over on the R side, you'll see how this works. I'm going to run this through, and you'll see one great thing about RStudio. It includes a plots viewer, and this plot viewer here shows the plot. And importantly, ggplot2 gives back SVG graphics, which short for scalable vector graphics. And that means that if I want to expand the plot and make it wider, I can do that. And or if I want to make it taller and more narrow, I can do that. And this gives me a lot of flexibility for working with this information. So I find that pretty useful to work with. And if you want to export out your plot then for just to kind of put into a report or tweet it out or share, you can right click and choose copy image or save image as, or alternatively, you can click the export button, save as image, and you'll get an export image dialog where you can go and decide the dimensions of your plot and where to put it. So the plot viewer and ggplot2 work extraordinarily well together, and it is a fantastic resource that allows us to do a lot of interesting visualization, which we'll be covering here. So what we're going to be going through is 3 different scenarios, if you will, for data visualization. The first one covers visualizing margins of error. So in the ACS, as we've discussed extensively to this point, and we'll continue to discuss extensively, ACS estimates include information on uncertainty. So we have in data that's returned by default in tidycensus, we have the estimate, the ACS estimate in the estimate column, and its associated margin of error in the MOE column. And so what this means is that when you're visualizing the estimates, you're visualizing kind of by definition based on whatever that reported value is, but that value isn't really a value per se. It represents a range characterized by uncertainty around that estimate. And so thinking through how to visualize that can sometimes be challenging because uncertainty is not something that a lot of people really understand all that well. And it is something that potentially can be even more difficult to represent on a chart. So let's take an example of visualizing data without reference to uncertainty. And what we're going to be doing is grabbing data on median household income for counties in New Jersey. So we specify here, yes, geography equals county. For the level of aggregation being counties. For the variable that we want, we're grabbing the variable ID code for median household income, which is SPE19013_001. State equals New Jersey, year equals 20. And we're gonna just do a little bit of extra data wrangling where we're using the str remove function from the stringer package to get rid of some extra information in the name column that we don't need. So the space county, New Jersey, that's common to every county in New Jersey, and we don't necessarily need that cluttering up our plot. We can then pass that to ggplot2, and this draws on an example that we covered really in the first workshop. So let me jump over here to our studio in just a moment and talk through it. We're going to be generating a plot that looks like this, that shows a ranking of counties by median household income in New Jersey from the 2016 to 2020 ACS. So let's go over to our studio and let's create that. So I first run through and I grab my New Jersey income data. I run this code. I get the data pretty quickly. I can open that up in my browser if I want. And so here we have all those counties with an estimate and a margin of error. I want to visualize this information in the estimate column, and I want to visualize it comparatively. And so just to talk you through what this code is doing, I initialize the ggplot object with a data set, New Jersey income. My aesthetic mapping is the estimate column mapped to the x-axis, and the name column mapped to the y-axis, but we're using reorder here to order our counties in order of estimate. So we'll get a chart that shows those counties in descending order, which makes it easier to parse. I then specify a geom function, which is geom call to make a bar chart. I use the labs function to modify the labels on the chart. So I give it a title, I give it a subtitle, then I modify the X and Y axis labels. I choose a theme. The default theme in ggplot2 is theme gray. I like theme minimal, which is a muted white theme. And I specify base size equals 14, which makes my text on the chart a little bit bigger. And then I use scale X continuous again, but I use a custom dollar format here. What this is basically doing is scaling my numbers down, then to the end. And so it's going to format it as dollars, but it's basically going to divide those dollars, as you can see, by 1,000, and it will then put a K on the end. So let's go ahead and take a look at that and see what it looks like. All right, we've got ourselves a chart. I'm going to make it just a little bit taller and a little bit wider. And it's reasonably informative. So it shows that Hunterdon County is the richest county in New Jersey as measured by median income. Cumberland County is the poorest. And Morris County and Somerset County come in just behind Hunterdon County with values that are very, very close. So second and third place. So here's my ranking of counties in New Jersey by median household income. The question arises then, is this ranking actually accurate? Does this actually reflect reality? Well, it reflects something that resembles what's true, but we have to remember that all of these estimates that we are visualizing are characterized by uncertainty. And we're not currently representing any uncertainty on this plot. So if we think about this, we can go back here and take a quick peek. And I have this code in here if we want to run it. A quick peek at the margins of error around these different estimates. So Hunterdon County comes in by what looks like about $600 or even $550 or so as having the highest median household income in New Jersey. But you'll notice that this $550 split is characterized by a margin of error. So the Hunterdon value of 117,858 is actually an estimate that we're 90% sure is about $4,300 more than that, or $4,300 less than that, somewhere in that range. And that range is large enough that Hunterdon County might not actually be the richest county by median household income in New Jersey. In fact, it might be Morris County, it might be Somerset County. All of these margins of error overlap. So here we have a situation in which we might be trying to show a stack ranking in New Jersey because of uncertainty in our data. That actual ranking might not be true. And you can imagine, headlines show Hunterdon County, wealthiest county in New Jersey. Well, it might not be. So how do you represent that in an intuitive way? A potential solution is to use what I'm calling here a margin of error plot. And what a margin of error plot does is it, instead of using the bars, it modifies the information on the chart to basically show error bars around each estimate. And so this is some extra code that's highlighted here. And I want to step you through basically bit by bit what this is doing. And we can layer on different elements to kind of see how this plays out and where we get to. And so, in fact, this may even be kind of a useful example for showing what the different layers ultimately look like. And so where we're trying to get to is a plot that looks like this. And we'll come back to that in just a moment, what that polished plot looks like. So let's think about this, and let's use this as an opportunity as well to talk through exactly how a ggplot2 graphic gets made. So what I'm actually going to do here is I am going to remove this assignment piece. You don't have to do that, but I'm just going to kind of iteratively step through these different layer steps to show you kind of how we go step by step and build out this graphic. So I have the same information here, NJ income, as my data set, and my same aesthetic mapping when I initialize the ggplot object. And so I can run through this first bit of code, and I run it. And what it does is it creates an empty plot. So that's what an empty ggplot object looks like. I have an aesthetic mapping where I have all of the counties on the y-axis, and I have the American Community Survey estimate on the x-axis, but I haven't told ggplot2 how to actually draw any information. What I'm using here is the geom error bar function, and I'm specifying a custom aesthetic here in which the minimum x value is the estimate value minus the margin of error, and the maximum x value is the estimate value plus the margin of error. So that's my range that I'm 90% sure the true value is within. I then can specify a width and a size to modify the output appearance of my error bars. So instead of drawing actual bars on the chart, I'm going to be drawing ranges that represent the estimated ranges within which the true value lies for each county. So let's take a look at how that appears. Here you go. I now have basically a chart that instead of showing actual bars that we're comparing, I'm showing error bars. This is the range within which we believe the true value of Hunterdon County's median household income value lies. This is the range for Morris County, and this is the range for Somerset County. And so we can say we're fairly sure that the county with the highest median household income in New Jersey is one of these three, because their margins of error, their little error bars, don't overlap any other counties in New Jersey. So it's one of these three. We're just not sure which one it is. We then see a ranking of the ranges, and Cumberland County here, we can be reasonably confident that Cumberland County has the lowest median household income in New Jersey because its margin of error doesn't overlap any other county. So this is helpful to a point. But it's still helpful to visualize the point estimate and the actual ACS estimate. So we can estimate on top of it. We could do this with bars if we wanted to, but I find it useful to do it with points, the dot plot instead. So for the point estimate, we actually use geom point and plot a point on top of it. And so we can add this geom point piece and add little circles on top of it. So I sometimes call this a TIE fighter plot because it looks like little TIE fighters from Star Wars with the point estimate in the middle, and then you have the error bars around it. But what this allows you to do is actually compare those point estimates, and it really visualizes that ranking in the ACS pretty well, but then it gives you the uncertainty around that. And you'll notice that I'm just setting the color to navy and the size to 3. You can modify that, choose a different color or choose a different size if you prefer a different look. These then labels on the chart, reorder name, comma, estimate for a y-axis label, not very informative. So I can add in this call to labs to change that. Now I have much more informative labels. I've added a little caption telling what the error bars mean. Theme minimal will change the theme of my plot to a white background. Make this a little bit taller. And then finally, these numbers may be okay, but let's format them a little bit to look like dollars. And so here we get our final plot. So hopefully this gives you a sense of a kind of proposed methodology here for visualizing margins of error comparatively in the ACS, but also it gives you a sense of how ggplot2 works, where you basically layer on different chart elements as you go, as you progress from original blank template initialized with the ggplot function to final plot that you're ready to show to other people. And I mean, you could continue to customize this even further. There's a lot that you could do with it. This scratches the surface in some ways, but it gives you a little bit of the genealogy of how a chart gets built. So moving forward, I want to go to the next use case, which is one of my favorite types of charts to build. And that's going to be the population pyramid. So population pyramids are extraordinarily, in my opinion, informative visualizations because they allow you to examine the comparative population structure of different areas. So population pyramids, if you're not familiar with them, are kind of side-by-side horizontal bar charts that reflect around a central axis. And we stack bar charts on top of each other. So each bar reflects an age cohort, the relative size of an age cohort. And then either side, sort of mirrored around the central axis of the chart, is going to represent the population size or percentage by sex. So it's an age and sex chart. And visualizing it in comparative context is really, really interesting. So, in my teaching, I'll use international population pyramids all the time to talk about areas that have kind of lots of migrant labor. It's pretty interesting to show aging areas in comparison with, say, college towns, which have very different population structures, center cities, suburbs, to think about, overall kind of life course and where people move to. And so being able to build out population pyramids, I think, is a great resource. They are reasonably complex charts to build, however, because it requires assembling a pretty large amount of data and making sure that you have that data in the right format in a way that makes sense. You have to figure out how to label the data. You have to figure out how to arrange the data the right way. And so I'm going to step you through step by step here, a recommended workflow for building population pyramids with ACS data. To get started, you need to find the data. And with respect to kind of age and sex information in the ACS, there are multiple resources you can look to. If you look at the table in the detailed ACS tables where you have age and sex breakdown, let's go over to our studio. We already pulled that in. So we had this data set, if I go further up, that I created called ACS vars. And that's all of the variables from the detailed tables in the 2016 to 2020. Yes, it's almost 28,000 variables. You'll notice that the very first table is actually age by sex, B01001. And from those of you who attended the first workshop, if you want to pull down all this data at once, you can use the table argument in getACS. If you were to say, getACS, geography equals whatever you want, table equals B01001. So taking the prefix and leaving off the suffix, it'll pull down all of the B01001 variables in one shot. So the table argument is a great one to use. We could use this data, but there are limits. For one, the age bands are not consistent. So the ACS gives us 5-year age bands, say for young children, but then it starts to split up the 5-year age bands for understandable reasons. We're thinking about, different years that are notable. We have 21 years is separated out by itself, but 10 to 14 is not. And if we want to build a population pyramid, we're going to want consistency in these cohorts, because if we're comparing a 1-year age band and a 5-year age band on a chart, the 1 year is going to have the smaller number, even if it's part of a cohort that's proportionally larger. And so we need to have that consistency. And so if we're using the ACS detailed tables, we would need to aggregate this information, which is an additional layer of complexity. One piece of advice when you're working with ACS data, and there are 28,000 variables in the detailed tables, it's a lot. Before you start pulling down ACS data from the detailed tables, before you do that, think about, what is the output that I want? Does it require aggregating my data in a sensible way? If it does, Census may have already pre-aggregated that data for me, and it's found in either the data profile or the subject tables. So thinking about age cohort by 5-year age bands, that's a pretty common use case. It's what you want for population pyramids. Is that found in a different data set? And in fact, it is. So if we go to the subject tables and we load in data from the subject tables, we can actually find pre-aggregated versions in a data set that's much smaller and easier to search. So if I run this code here, I'm going to go back down and load in the subject tables. It's very fast to load those variables. Close these out. I take a look at my subject tables, and well, I have 5-year age bands right there, and they're pre-aggregated for me. The subject tables, yeah, it still has 18,000 variables in it. The data profile is even more parsimonious, so maybe 1,000 or so. But what this gives me in many cases are pre-aggregated statistics to save me a step. So here I have total population, 5-year age bands. I scroll down, I get percentages. So if I want percent of the total population instead of just raw total population, that's already pre-computed for me. I don't need to go find an appropriate denominator. And a great thing is, it gives me a derived margin of error around that percentage already. So I don't need to derive that margin of error myself. I don't want to. I continue to scroll down, and this is where it starts to break it out by age, by sex. So here we have males by 5-year age cohort. And here we have, if we continue to go down, here we have females. So once I've identified the variables that I need from the subject tables, I'm going to want to make a custom pull to getACS, or a custom call to getACS to get the specific variables I need. And this is where some extra R programming skills can come in handy. You could go in and you could manually type out these variable IDs and get them in one fell swoop. You could pull down the entire table too if you wanted to, but that is still going to leave you with extra variables you don't need, and you'll need to filter those out. So what I'm going to do is apply a little bit of programming knowledge, show you some tricks that I tend to use to assemble variable IDs. And so what I'm going to do is prepare my data request. I'm going to set up a set of cohort names that I've pre-written. And these are custom labels that I want to supply to GetACS. I'm going to show you how this works in just a moment. I'm then going to use this code here, which is a little bit more complex, but I'm going to step you through it, to get sequences of variable IDs called vectors that I can send to GetACS. So I have my male variables and my female variables. You'll notice in the subject tables for female, the female variables I need are S0101 underscore C05 underscore 002 through 019. That's what I want. So I have those suffixes with a common prefix. What I'm doing here is taking a sequence of numbers. So if I type in R2 to 19 with a colon, it'll give me a sequence of integers from the first number to the last. I take that and then I use this strpad function from the stringer package, which is one you want to know, that will pad my data. In this particular case, I'm left padding these numbers with zeros. So I'm going to show you basically the intermediate steps here. So now I've left padded all the numbers with zeros. I then use the paste zero operator, which basically stitches two strings together to tack on the first part of the variable ID to this suffix. And the dot in the pipeline refers to the information that is being passed to it. So now I have all the variable IDs. The last step that I'm going to do is I'm going to use set names to name each of these elements. I'm going to show you why this is important in just a moment. So running all this through, my male variables looks like this. I have all of the appropriate variables, and they are named by their age cohort. I'm going to do the same for females. So what can I use this information for? My next step is, now that I have this sequence of variables, I can send this to GetACS to get data for each of those variables in a nicely formatted, tidy data frame. My data assembly is going to look like this. I'm going to step you through step by step how we're preparing data for the pyramid. My first call, I'm going to make two separate calls to GetACS to do this. The first is I'm going to create a data set called male data. And you'll see why I want to kind of separate those out just for purposes of illustration. For my male data, I'm saying geography equals county. I want Washtenaw County, Michigan, which is where the University of Michigan in Ann Arbor is located. And I'm getting my male variables for the 2016 to 2020 ACS. I'm then creating a new sex column with mutate. And notably, I am multiplying my ACS estimate by -1. Why would I do that? I'll explain that in just a moment. I then do the same for females, but I don't multiply the estimate by -1. And then finally, I use the bind rows function from the tidyverse to combine my data and then convert the variable column to something called a factor. Let me step you through this and explain this in greater detail. So my first step is to grab my mail data. And I'm just going to grab, just for purposes of illustration, I'm going to grab it without running it just yet. I open up the mail data object. And the thing is, the way that we formatted these variables with names, if you pass a named vector to get ACS, it will replace the ACS variable IDs with the names that you plugged in. So now I have appropriate cohort names instead of the variable IDs. My next step is I'm going to redo this, but multiply the estimate with a negative number. And I see that Ricardo just answered this question, why we do that, in the chat. I make these numbers negative because I want them to be plotted. I want the males and the females to be reflected around a central axis. So I need one sex to be negative and basically plotted center to left, and the other sex to be positive, plotted center to right. I grab this information for females as well, and then I combine the result, giving me my pyramid data. The factor function, so factors in R, order data according to a set of levels. So by default, these names will be interpreted in basically alphanumeric order, which won't work for the cohort names because it'll basically go 0 to 4, 10 to 14, 15 to 19, and it'll stick 5 to 9 in between 45 to 49 and 50 to 54 because it's trying to do it in alphanumeric order. So we need to manually override that and create a factor. Our variable column is a factor that honors this ordering that we're giving to it. So I open up my pyramid data, and I see that I have males with negative numbers and females with positive numbers for each age cohort. I then build out the population pyramid. And the population pyramid, honestly, is not that much different than the bar chart that we created earlier. What I'm doing here is I'm creating the pyramid, mapping the estimate column to the x-axis and the variable column to the y-axis. And I'm specifying a fill aesthetic as well. So I want different colors for the different sexes. I'm using geom_call to make a bar chart. And a couple different things. It's continuous. I'm specifying a custom label formatter. This is a little bit tricky. You don't want negative numbers on your x-axis. You want to show positive numbers. And so in this particular case, you'll want the actual label to be the absolute value of that number. And so you can read this as, for every label x, take the absolute value of whatever that number is divided by 1,000, and then tack on, using the paste 0 function, a k to the end of it. I then use scale fill manual, which we haven't done yet, to specify a custom color fill. And I'm using maize and blue taken right from the University of Michigan website to reflect the university in Washtenaw County. Let's run this code through. Take a look at what we get. I'm going to make actually this size a little bit smaller. Your base size is going to depend on your monitor, what shows up. So I'm actually going to make this the font just a little bit smaller. But here's my population pyramid with University of Michigan colors, appropriately ordered. And like most college towns, this is what the structure tends to look like. where you have this bulge of 20 to 24-year-olds and 15 to 19-year-olds, and other age cohorts are much smaller in comparison. So this is a fun one. You could try this out for a county of your choosing, and they are, you'll see very, very different age cohorts. And yes, the population pyramid code is a bit complicated, but a great advantage of this is now you have a workflow to build out a pyramid. And all you really need to do is change the state and the county, and that will create an appropriate pyramid for you. It might change things a little bit if you have a really big county, or really small county. The thousands for a really small county won't necessarily make sense, so you might need to modify that. But in most other cases, this code will work pretty well for medium to large counties. All right. So in the last example that we're going to run through before we break is mapping ACS data. And I'm going to go through this at a reasonable pace, in part because we spent an entire workshop going through, and we basically spent an entire workshop going through mapping census data, and all of those examples applied just fine. So with respect to mapping census data, we learned all about that last week. Participants learned how to make maps of decennial census data focusing on TMAP. What we're going to focus on here is mapping with ggplot2 and show you how to do that. For those of you who are new and you want to map spatial data, review the slides, review the workshop materials from last week. But also, if you add geometry equals true to a tidycensus function call, so in getACS, it fetches the shapes for your geographies, pre-joins them together, and gives you back a spatial object for mapping without any additional fuss. It is the reason why I wrote tidycensus, because I was tired of doing this manually, and it works pretty well in my opinion. So let's go through this. What we're going to do is we're going to map median household income for Orleans Parish, Louisiana. So this is where New Orleans is located. We're going to pull down this information using state equals Louisiana. Even though counties are called parishes in Louisiana, we still use the county argument. And we're specifying geometry equals true to get this information at the census tract level. And this is what our data set will look like. So let's go ahead and jump back over to our studio and grab it. If you haven't used this before, literally the process that takes my intro to GIS students days sometimes to accomplish, we accomplished in a second. Grabbing census data, grabbing spatial data, combining it, and getting back a result. And so once we have this information, we can start making some maps. And so in the last workshop, you learned how to use the TMAP R package to accomplish basic mapping tasks. You can do the same thing in ggplot2 with the geom_sf function. And so what geom_sf does is it allows us to quickly make exploratory maps with ggplot2. And all you need is a geographic object formatted as a simple features object, which is returned by tidycensus. And you use that as your data argument in ggplot. And then optionally, you can specify a fill aesthetic to color in the different polygons, the different census tracts based on a column in your data set. This will create what's called a choropleth map, which is a shaded map in which values in the data are mapped to a color palette. So in this particular case, higher incomes are going to be lighter blues, lower incomes are going to be darker blues, and you can make that map pretty quickly. So let's go ahead in our studio and create that map. I click run. And here I have the very first map. It's not polished yet, but from an exploratory standpoint, it's pretty useful. If I know New Orleans, I can see these areas and make comparisons. So we're going to step through polishing this up. In the next step, we're going to add an option to modify the color palette. With the scale fill family of functions in ggplot2, you can specify a different color fill for your census tracts. And there are a ton of different options available. So the popular color brewer color palettes for mapping are available, and the popular Viridis color palettes for data visualization are also available that are pretty fantastic for making maps. So I'm using scale fill Viridis _C for a continuous version of a Viridis color palette. And I'm using the Mako option, which ranges from like a dark blue to a light green, to modify the color palette on my map. And this is something that's fun to experiment with, find a color palette that you really like. So just to show you a few examples, this is the Mako color palette. There are a bunch of different options. If you search for the Viridis and the Viridis Lite R package, you'll be able to find all those options. For example, the core Viridis palette is very popular. So if I type in option equals Viridis, that'll use this sort of purple to yellow palette. There's another one, option equals Inferno. That'll use this sort of dark purple to really bright yellow, but going through sort of some magentas and oranges to get there. So there are a lot of different options that allow you to create pretty custom maps. So I'm going to change this back to Mako. Over there. So one thing that you could do is you could start from here and create a map. I'm going to tack on a different theme void you'll often use for cartography, and that will remove all of the elements except for the legend. So if you don't want this latitude and longitude, if you don't want the grid behind it, you can use theme void to void all that out. And now, in many cases, this is a kind of plot that is useful to me. The tricky thing about a place like New Orleans, however, and Orleans Parish, Louisiana, is you have a ton of water area that's covered by census tracts. And this water area, it kind of obscures what the region really looks like. And so in this particular case, we might want to do some extra modification of the geometries to remove the water area and make the map look a little bit better. And so I'm going to show you an example. This is a brand new example that I just added to the tidyverse R package that's more advanced. So we covered this in last week's workshop. So review those materials if you want to get more in-depth information about it. And I'll also be adding a section on this to my book very soon. What we're going to do here is we're going to re-pull down the data. And just kind of going back, I'll talk through this on the slide side. We're going to pull down the data with a couple different options. We're going to set CB equals false to pull in the core tiger line shapefiles. What that means is that these are sort of the original shapefiles before the ones that are clipped down to the US coastline, used by default in tidycensus. What that will allow us to do is avoid sliver polygons when we're using this erase water function. We set a very high area threshold. So we'll take the top 1% of water areas by size and erase them from our polygons. And so if you're using our Studio Cloud, unfortunately, we only have 1 GB of memory in our Studio Cloud. This will crash your session. So just, I would say, put this on pause and try it out when you have R in our Studio installed on your machine. I'm going to run this through. It's going to take a few moments to do because there's a lot of water area around New Orleans. And so this is going to take a few moments to run. But erase water is really cool because it automatically detects the appropriate water area. It uses the tidyverse package to pull in water shapes and then removes that water area from your census tracts and then gives you back a data set that looks a whole lot better and kind of more intuitive with water area removed. So this will take a few moments to run because there's so many bodies of water in the New Orleans area. But eventually I want to show you what we're going to get to. So we go back to the slides and we'll come back to our studio in just a moment. We're going to create a map like this. where, as you can see, we have water area removed from the polygons. You still have some areas where you might have some marshland and you don't have an income estimate, but now we get a much more realistic portrait of the parish. And so jumping back, I would say for most locations, this is going to be reasonably fast. New Orleans, it's just going to take a minute because you have so much. That you are erasing. So we can take a quick look at this. Now we have a much kind of nicer looking map. The last bit, the last piece in this section of the workshop, and if you know New Orleans, but I don't personally know New Orleans. I've actually never been there. And so I might need a little bit of extra reference. And in the previous workshop, we covered the process of adding a base map to TMap maps. It's even easier in ggplot2 than it is in TMap. You can use the GG spatial package and add a call to annotation map tile, which will auto detect the extent of your data and pull in map tiles for use as a base map, and then plot your shapes on top of your base map. And we're using the OpenStreetMap tiles styled by the Cardo web mapping company to do that. And it really doesn't take that long to put this together. So I'm going to go ahead and run this code. It's going to pull down map tiles from the Cardo OpenStreetMap server at the zoom level of 11. It's going to plot my data on top of it. And when it's done, I have a much nicer looking map that's styled. And it shows where New Orleans is. And it shows that kind of nice base map reference with a cleaned up map. All right, so that's the end of part 2 of the workshop. Again, if you're using our Studio Cloud, this is more memory intensive, so it will crash your session. But try it out when you get R in our Studio installed on your own machines. And so now we have a much nicer looking map, nice base map, clipped with that water area removed. So I'm pretty excited about this feature. It's been around for about a month now in the tidyverse package. So let's break for, let's say 7 or 8 minutes, come back at 107, 108 Eastern time. And in that interim, feel free to try recreating one of the chart section, but use a different state or a different county, and then try customizing maybe with a different theme or modifying the colors or styles like I demonstrated. So we'll come back, cover a few questions at the beginning of the next session. Let's come back in 6 or 7 minutes. Now, we're in this section, part 3, we're going to cover margins of error. So hopefully answer a number of your margin of error questions in this section. Really more advanced topics with respect to margin of error. And then we're going to cover time series analysis, which is a challenging topic to deal with when you're working with census data for a variety of reasons. This is a more conceptually and technically advanced section of the workshop. So if you are new to census data and you're new to R, there's still going to be a lot in here that I think will be valuable to you. But there might be some new techniques and some new concepts. So just be mindful of that, especially when we get toward the end, we're going to show a fairly advanced use case. So let's discuss. Tidycensus is opinionated in that it always returns the margin of error for an estimate when applicable. Now, not all estimates have margins of error associated with them, but when they do, tidycensus, I made the decision when developing it that estimates need to be understood in the context of their margin of error. And so even though the estimate and margin of error are treated in the census API as separate variables, I don't treat them that way. You always will get both back. This is great because it allows us to visualize and quantify uncertainty, but I mean, it is uncertainty and we need to be mindful of that. Mentioned this earlier, but due to the COVID-19 pandemic, census had a real tough time conducting the 2020 ACS, and the response rate was only about 2/3 of what it typically is for other ACS years. What this means is that your margins of error in the 2016 to 2020 ACS incorporate this additional uncertainty from the smaller sample size in 2020. And so your margins of error tend to be proportionally larger than in previous data sets. And I took a crack at this when the data came out, just making a comparative box plot. This is from the median household income estimate for all census tracts in the state of Texas. And I pulled the data down for 2012 to 2016 through 2016 to 2020 ACS. And I calculated the margin of error as a proportion of the median household income estimate. So basically, what you have here is the margin of error if it's 25% of the median household income estimate at the census tract level, then that's going to come in at about 0.25. And as you can see, for end years of 2016 through 2019, the margins of error as proportions of the estimate tend to be relatively consistent. 2020 is different. You can see the median value is slightly higher. And you look at the interquartile range of that 2020 box plot, it's bigger. So what you have is a situation in which your margins of error are going to be bumped up, and census said maybe by 10 to 20% across your variables. So it's great that we have the data, but just be mindful of this. 2020, it sounds like the ACS went better in 2021 than it did in 2020, and hopefully we'll be getting back more to normal in 2022. But be mindful of this. The next several years, the COVID-19 pandemic is going to be influencing our data quality. And so we're going to have larger margins of error around our estimates for the next several years of ACS data. And so when thinking about margins of error, there are a variety of different things that you can do with your MOEs. By default, as we've talked about before, your MOEs are going to be coming back in the MOE column. In wide form data, your MOEs are going to be spread across the columns with your variable name with the suffix of M. Now, by default, the American Community Survey returns data with margins of error at a 90% confidence level. I've discussed this already. It means we're 90% sure that the true value is in a range of the reported estimate plus the margin of error, or the reported estimate minus the margin of error. If you want to create different confidence levels, so basically where you're 95% sure or 99% sure that the estimate is in this range, you can use the MOE level argument in GetACS to modify this. And so to show you briefly how this works, I'm going to jump back over here to RStudio and grab, honestly, let's think of a good example data set. Why don't we do our New Jersey income data? So here's our New Jersey income data. You'll notice here, let's look at Atlantic County. So the estimate is 63,680 with a margin of error of 2011 of about $2,000. If if I were to add the argument MOE level equals 99, what that will do is modify the returned margin of error to reflect a 99% confidence level around the estimate. So I'm going to rerun this code and then take another peek at my New Jersey income data, and notice that now that my margin of error has bumped up to 3,100. So I was about 2,000 before, now I'm 3,100. So my margins of error are larger. But now I can say I'm 99% sure that the true value is somewhere plus or minus $3,100 of this ACS estimate. So if you want that additional certainty and to increase your margins of error, you can choose a different MOE level. And in turn, we can use this and we can create a margin of error plot again. So why don't I just recreate this? So here is my margin of error plot with the bigger margin of error ranges included. All right, so let's go back down here and let's head back to the slides. Margins of error for counties are one thing. We can handle that reasonably. For small geographies, margins of error can be a problem. For tracts or for block groups for small populations, especially in the 2016 to 2020 ACS, your margins of error might be proportionally pretty large. So I have an example here to illustrate. I'm pulling down data from the detailed tables on age bands by sex, granular age bands by sex. So sometimes there are 2-year age bands, sometimes 5-year, for a specific census tract that I'm calling example tract in Salt Lake County, Utah. So if you run this code, again, this tract is not meaningful in any particular way. It's used for purposes of illustration. And let's go ahead and take a look at that data. So I'm going to jump back here to our studio and run that data through, and let's take a peek at it. So this is my data for my example census tract for population age 65 and up in granular age bands, and take a look at the estimates and the margins of error. For many of these age groups, the margin of error exceeds the estimate. So for example, the first bracket, I believe, is males age 65 and 66. We had about 12 of those, plus or minus 13. So minus 13, that goes into negative numbers. So your floor is going to be 0 there. But, in some other age brackets, we have estimates of 0, or here's an estimate of 5 with a margin of error of 8. So very large margins of error. And this is where the ACS, you have to take it as it is. ACS estimates are estimates. You can think of the characteristics that are designed to be used in a comparative sense, kind of in the way that we're doing comparisons here with our household income plot. They are not true counts. You should not show up in this census tract and say, oh, there are X number of people in this age group because the ACS said so. Therefore, I'm going to use that to kind of, bring a certain number of pamphlets for registration in this program. It's different than the decennial census is intended to do in that way. These are interpreted characteristics, not true counts. And so you use them in a comparative context. That is how this intends it. But when you're dealing with these very small geographies with very small populations, this is an issue that can arise. So something to think about alternative ways of working with your data. And I'll introduce a couple of different methods for thinking about this. So in many cases, when you're working with data from the ACS, you need to derive estimates. So maybe you're saying, well, I want to calculate a percentage. And what you'll do then is, divide a value by a numerator by a denominator to get a percentage or proportion. But how do you handle that with respect to the margin of error? Well, the Census Bureau publishes documentation on how to calculate derived margins of error for sums, products, ratios, and proportions. And what I've done is I've incorporated that into tidycensus with the MOE sum, MOE product, MOE ratio, and MOE proportion functions. And so basically what that does is, if you are trying to calculate, let's say, a proportion from 2 estimates, and you have the margins of error around those estimates, you can supply those margins of error and get, using the recommended formula from the US Census Bureau, a derived margin of error along with it. So the example that I include in the slides is just a very simple example of how to use the MOE proportion function. And so what MOE proportion does, and I can bring that up in the help documentation. If you're new to R and you want to take a look at the help documentation for any function, type in a question mark in your R console and then the name of the function. So I'm going to type in MOE prop, and that will bring up the documentation. So it's designed to calculate the margin of error for derived proportion, and its arguments are num, denom for numerator and denominator, and then MOE and MOE denom for MOE, and for the numerator, the MOE, and the denominator, the MOE. All these functions are vectorized, so you can run them over a data set if you want to, if you have different columns. In this particular case, we're going to use the simplest example. So let's say we have a numerator of 25 and then a denominator of 100. So let's say 25 is the number of, let's say, white people in a census tract, and we want to get the proportion of the population that's white, and the total population is 100. The margin of error around our estimate of white people is 5. Our margin of error around the total population is 3. So I can calculate MOE prop with my numerator, denominator, margin of error, numerator, and margin of error, denominator. And I run that through, and I get the result, which is about 0.05. So my derived estimate is 0.25, and my margin of error around that estimate is about 0.05. So I can take this a step further and embed it into workflows designed to work with margins of error in a tidyverse context. And this is just scratching the surface in this particular context, but one solution to dealing with large margins of error is to roll up your data and aggregate it up. And there's some pretty interesting research on aggregating geographically. You can also aggregate by category. And so here I'm using MOE sum inside of a group by summarize tidyverse pipeline. And so what I'm doing is I'm specifying here, I'm rolling up by sex, basically. And so I'm using some code here with the case when function. It's a little bit more advanced to say, okay, some of these variables reflect males, others reflect females. Let's create a new sex column to show that. We'll group by our census tract ID and the sex column, and then create new derived columns that sum up within these groups. The estimate column, that's going to be our new derived estimate. And then we use the MOE sum function, which takes 2 arguments, the margin of error and the estimate, to create a derived margin of error. And so if we run this through, we can take a look at our data. We've now rolled up our information, and this reflects males and females by census tract over the 85. And you'll notice that margins of error, while still large, are much more reasonable. They're not exceeding the estimates anymore. So this is one such solution for dealing with large margins of error relative to the estimates. Roll your data up, either potentially aggregating geographically or aggregating by group, and just kind of dealing with those large groups if you are uncomfortable with the level of uncertainty in the data. That said, I showed you before the subject tables in the data profile. That is the first place that you look in these circumstances. So the US Census Bureau, and I quote, all derived MOE methods are approximations and users should be cautious in using them. This is because do not consider the correlation or covariance between the estimates. So they might be overestimated depending on whether the basic estimates are correlated in positive or negative direction. And so what this means is if you find yourself needing to aggregate up, the first thing you should do is see if that aggregation already exists in the data profile or subject tables. If it does, use that, because Census has already computed a correct margin of error for you that is going to be more accurate than the derived margin of error that you might compute. Now, granted, you will sometimes need custom tabulations that are not in the subject tables or data profile, and that's where you reach for these methods instead. So population over age 65 by sex, that's in the subject tables, and I think the data profile, that's where you should go first. All right, so that's our discussion around margins of error. I want to spend some time now with time series analysis, because this is a big topic that a lot of people are interested in with respect to ACS data. It's also a hard topic. It's a challenging conceptual and methodological topic to manage, and we're going to try to approach that with some different methodologies here. So when you're working with ACS data, census cautions against making temporal comparisons between overlapping survey years, because you're basically baking in the same data on one side of each comparison. What they recommend doing for 5-year ACS comparisons is to compare discrete 5-year ACS periods. So compare non-overlapping data sets. So for 2016 to 2020 data, you can compare back to 2011 to 2015 or 2006 to 2010. Those are appropriate samples to compare with. Census doesn't recommend, say, comparing 2013 to 2017 with 2016 to 2020, because both are kind of baking in information from the same ACS data sets. So there are a couple of different ways that we can get time series information in the ACS. And one way that you can accomplish this is with a little bit more advanced programming. And one of my favorite packages in R is the PER package for functional programming. It's also a hard package to learn. So if you are new to R, bear with me here, because conceptually, we'll step this to tell you how it works. If you're trying to build out a time series of ACS data, the map DFR function in the PER package, which is a member of the tidyverse, is your friend. What it does is it iterates over a sequence. So it steps through a sequence of values, calls a function for each of those values, and then combines the result into a nice data frame. So let's say, for example, we want to look at changes in median age by county over time in the state of Nebraska. We could go through and use getACS. We could grab that for 2010, grab it for 2015, grab it for 2020, assemble the result manually, and that wouldn't be too onerous. What MapDFR allows you to do is take a sequence of years here, 2010, 2015, and 2020. It iterates over those years. So you can think of that for each of these years, apply this function. And the function is just getACS, where we add a new column where we set the year to the year value. So it pulls down median age, and then in the derived result, let's go ahead and sort it by name so we can see what we're looking at. That ultimately gets us something that looks like this. And let's head over back to the R side and show you how that works. It'll make 3 separate pulls from ACS, happens instantaneously. We can take a look at our Nebraska series in our data browser. And hey, look, this is interesting. We now have 3 different end years where we can compare counties in Nebraska to see if there are any that are getting older and any that are getting younger. For example, Boyd County is getting a lot older. It went from median age of 47 to 56.2 in 2020. Some other counties like Buffalo County are fairly consistent. So this is a great way to get started doing some time series analysis. But there are some cautions. Sometimes people have asked me, well, can you just bake this functionality into tidycensus and allow me to pull multiple years at once? And I've always said no. The reason why is not all variables stay consistent from year to year. So be very cautious when you're using this method. The detailed tables, those variables will be consistent from year to year, but not all detailed tables variables are available in every year. The data profile and subject tables, those variables change from year to year. So there's some consistency, which makes it confusing, but if they add tables, Sometimes they'll add them in the middle and then bump other variables down. Here's an example, and this is something that has bit me before when I was working on a client project, when I was updating all my code from 2018 to 2019. The data profile variable DP02_0068P gives you the percent of the population age 25 and up with a bachelor's degree in the 2016 to 2020 ACS. Let's swap this in to our Nebraska series code as the variable. And this is sort of an interesting comparison to make. Oh, you know, are counties getting more educated or less educated over time? Let's run it and take a look. So I'm rerunning. My code works, so I think that seems great. Let's pull up our Nebraska series and look at this. Adams County, 23,537, 24,042, and then 25.6. These first two values are clearly not percentages. So that is extraordinarily confusing. Antelope County, 5,124% of the population age 25 and up has a bachelor's degree. That doesn't make any sense. This is because the variable changed. And so be mindful of this. I believe this reflects the civilian population in a table about civilian and veteran status. It doesn't reflect educational attainment percentage until the 2020. So it's 0067P that is used in those prior data sets. And I could make a big mistake if I'm running an analytic pipeline based on this. So you have to be careful about that. An alternative, however, is something I just built into tidycensus this week. So it won't work if you have the CRAN version of tidycensus installed. You need the development version installed. I just added support for the ACS comparison profile, which is a special data set in the ACS that allows you to get data for a given ACS year, 5 years data set, and then the previous non-overlapping ACS data set in the same call. It's pretty cool. And so I think I'm close to finalizing this methodology. This is very much an in-development feature, but what I can do is I can grab inflation-adjusted median household income for 2011 to 2015 and 2016 to 2020 for counties in Alaska. These are the codes. I'm using a named vector to replace these variable codes. Again, if you have the CRAN version of tidycensus, this won't work. But I can run this through and hit the comparison profile and compare inflation-adjusted incomes. Let's make sure this runs. There we go. I'm comparing inflation-adjusted incomes for counties in Alaska between the 2011 to 2015 ACS and the 2016 to 2020 ACS. So in Aleutians West, adjusting for inflation, we saw income go down. We saw the same thing happen, it looks like, in Juneau. And so I still haven't played around with this feature a ton. I just published it a few days ago, but I'm pretty excited about this as a potential feature for time series work. So in these examples, we've talked about some of the caveats and some of the methods that you can use for time series analysis in the ACS. What we have worked with to this point is county level and up, and counties tend to be reasonably consistent over time, though not always. Alaska changes its county equivalents all the time. And so if you're working with Alaska, you're almost never going to have the same set of counties from census to census. In other cases, census names can change, county names can change, and in some cases, new counties are created. And so for that reason, the comparison profile only goes down to the county level. But in many cases, we want neighborhood level change. And this is tricky. I said this at the beginning of the presentation that the 2016 to 2020 ACS uses 2020 census geographies. And with each decennial US Census, the Census Bureau redraws its geographies for census tracts, block groups, and blocks, which means that if you're trying to make time series comparisons across, say, the 2011 to 2015 ACS and the 2016 to 2020 ACS, you can't neatly do that because the census tracts have all changed. They haven't all changed, but the overall kind of tessellation of them has changed. And so you won't necessarily have the same geographies or the same geography identifiers from ACS to ACS. So how do you handle this? I'm going to show you a couple methods for thinking through this. But this is particularly acute if you're working in a location that has had massive population change, so significant population decline or significant population growth. What the Census Bureau tries to do is keep census tracts at about an average of 4,000 people when they redraw them. But as you can imagine, 10 years is a long time for population growth. And so if you have a really fast growing area, like suburban Collin County, Texas, which I'll show in the next slide, outside of Dallas, you're going to have some census tracts that went from maybe 4,000 people in 2010 to 20 to 25,000 people in 2020 because a whole bunch of new subdivisions were built there. And so now you have a census tract that at 2020 geographies has 20,000 people. And if you're optimizing each tract to have about 4,000 people in the 2020 definition, it's probably going to be 5 census tracts divided up into 5 census tracts now. And it's not necessarily a clean division every time because let's say there's a new highway built in between 2010 and 2020. Census tries to draw census tracts that conform with major boundaries, like a new highway. And so it might subdivide up a census tract based on that. So here are tracts by total population in 2019. This is the 2015 to 2019 ACS and the 2016 to 2020 ACS. And so you can see here this bright yellow tract in Collin County. Well, it's been chopped up now into multiple census tracts for the 2016 to 2020 ACS. Really, any of the locations that have really large populations have comparatively smaller populations in the next ACS. It's not because they lost population, it's because they gained population. But you can show these maps side by side and someone might say, whoa, did the population decline in this area? No, it's just that we've redrawn the geographies. And so how do we deal with this from an analytics standpoint? We need some more advanced methods, and they're not perfect, but I want to show you a couple. When we're transferring data from one set of geographies to another set of geographies, we use a method called interpolation. And interpolation is used to basically estimate how to allocate information from one set of incongruent zones to another. It's a challenging method. So let's think of but let's grab some data and think of a use case here that makes sense. We want to compare at the census tract level changes in the workforce who's working from home. Because 2020 ACS, we're starting to get information on the pandemic. And so you might have more telecommuters and more people working from home, even filtering into this data set. Let's look at it for the Phoenix area. We'll grab for Maricopa County, Arizona. And so the variable that we're using is B08006017. We'll grab for the 2015 ACS, 2016, 2020 ACS. We're using ST transform. For those of you who are new to R, this is more advanced. What we're doing is we're using something called the projected coordinate system, which is a topic that is really beyond the scope of our conversation today, but just in a nutshell, we're representing data in a way that's appropriate, our spatial data in a way that's appropriate for the Phoenix area, and this will speed up our analytics quite a bit. So let's go ahead and pull that data down and take a quick look at it. So if I look at my environment, I've got a ton of objects now, but I have work from home 15 and work from home 20. You'll notice that there were 916 census tracts defined in Maricopa County for 2010 census, which was used by 2011 to 2015 ACS. For the 2020 census, we've added almost 1,000. We've added almost 100 census tracts. We have over 1,000 census tracts now. This means that our geographies in some locations may be similar, but in other locations are going to be reasonably different. And if we're trying to make temporal comparisons, we have to figure out an interpolation method that makes sense. I'm going to introduce two methods to you. One is already built into tools that you have. One, I just wrote the code for this workshop, and to the best of my knowledge, it's not found in any R packages. So I will discuss it with you in just a moment. The first method, and this is maybe the most common method that's used for interpolating data between inconsistent boundary sets. It's called area-weighted interpolation. And what it does is it takes a look at the intersections between two overlapping spatial data sets, and it computes weights for transferring data between those data sets. Area-weighted interpolation is often used because it's conceptually fairly simple. Basically, let's say you have a census tract with 1,000 people that is divided up into 5. Well, here's a better example: a census tract with 20,000 people that is divided up into 5 census tracts. And so those census tracts each have an area. And so what you do is you look at the proportion of the area of each tract, and you compare that to the parent census tract. And let's say one census tract comprises 50% of the area of the parent census tract. That would give it a weight of 0.5. And then you would multiply that weight by the original population value, basically saying, well, it's 50% of the area of the parent census tract. Therefore, we think that 50% of the population lives there. This can be a problematic assumption for reasons that we'll discuss in a little bit. It's typically more accurate when you're interpolating backward. So you're going in, like in a fast-growing area where you've subdivided up a bunch of tracts. In many cases, not all, in many cases, you're subdividing parent tracts into children tracts. And so what this will do is if you go backward from more census tracts to fewer, in many cases, area-weighted interpolation will accurately roll up those estimates within their tracts. It's not perfect, but we can use it. So if we're, in this case, by going backward, what I mean is taking our 2016 to 2020 data and going backward to the 2011 to 2015 geographies. So the 2020 tracks to 2010 tracks. We can implement that in the SF package with the st-interpolate AW function. And what you want to do first is just select the column that you want, because it'll try to compute it over every column. And if you have non-numeric columns in there, the function will fail. So what we're doing is we're taking our work from home 2020 data, and we're transferring it backwards to the 2010 geographies. And so basically what that does then is creates a calculation where you can make comparisons. And so let's take a look at how that works. And we're going to use the map view and leaf sync packages to create synced maps that we can browse. So let's run this through. Just take a moment to compute. So the sync function in the leaf sync package is really, really cool because it creates synced up maps where you can go in and they both move together. So the left-hand side is 2020 geographies and the right-hand side is 2015 geographies. So you can think of the left-hand side as the from and the right-hand side as the to. And so out in sort of Gilbert Chandler area, down here in southeastern Maricopa, this is where we did a lot of subdivision. So you'll notice here, this big census tract in 2020 was subdivided up into a bunch of smaller census tracts. Or I should say this big census tract in 2010, I meant to say, was subdivided up into a bunch of smaller tracts in 2020. And so what we did with area weighted interpolation, we looked at this parent census tract, which, as you can see, looks like there are 1, 2, 3, 4, 5 children census tracts, maybe with some small overlap with others. And the area weighted interpolation computes the proportion of this big census tract that each of these smaller census tracts constitutes, and then functionally rolls up that data accordingly. And so in this case, we're basically kind of adding up, we're summing up these tracks and getting an output estimate here as we roll up. And that's why going backward is a little bit more accurate for area weighted interpolation than going forward. Going forward is tricky when using area weighted interpolation because it makes the assumption that population distributions will be proportional to area. And in many cases, this is the opposite of what's true, because large census tracts are often rural areas or low density areas. So you have more people in the smaller areas, and that just sort of makes sense. I have my densely populated area, which has a lot of people, and then I have my low density area, which has fewer people. But area weighted interpolation allocates more people to the larger area when it should be allocating to the smaller area. So this is tricky, especially when you're going forward. And so if you're going forward, a better method is to use some other sort of weight. And a method that I am showing here that is really, it's not brand new, but it doesn't have a lot of implementations, is called population weighted interpolation, where you use some underlying description of a population, an underlying population surface, using a data set that explains the population distribution at a small geography. And so I'm going to show you how to do this for population weighted interpolation that uses block population weights from the 2020 census. We call this block centroid weighted allocation. If any of you have ever used Esri's business analyst software, this is the method that they do. So if you draw, say, a buffer zone or a travel time area, you can compute up in Esri's business analyst software the estimated number of people within that irregular shape. They use block weighted allocation, which is a method of population weighted interpolation that I've implemented here to do this sort of transfer of data between zones. And so to get this to work, it's a more advanced example. I didn't want to step through it step by step because it includes a lot of information. So I wrote a script that is included in the workshop folder called population weighted interpolation.r with a function called interpolate PW. And just to step you through briefly what it does. So I'm going to look in my files browser and you'll find the script population weighted interpolation. It is a function that takes a from data set and a to data set. So we're taking a from set of geographies and a to set of geographies. It identifies an ID column that will be retained. And then for all of the numeric information, it will attempt to do block weighted population weighted interpolation between the geographies. The extensive argument, if true, gives you a weighted sum. If it's false, it gives you a weighted mean. So if you have estimated counts, you'll want the weighted sum. If you have an estimated, say, median already, or an average, or a percentage, that's where you want the weighted mean. The weights are going to be, you can give to it whatever weights you want. What I'm using is block populations, which you can get from the tidyverse R package, and then you specify a weight column. This is more advanced R code in here, so I'm not going to step through all of it. But if you want to try this out, and hopefully it'll work on all your systems, it's working on mine, you need to click the open the script and click the source button, and that will define the function. So now I have the function. I then go back to my code, and I'm going to pull down a block data set for Maricopa County, Arizona. This might be a little slow. It'll be fast for me because I already have it pre-cached, so bear with me. And I'm going to go ahead and compute the interpolation. So I'm bringing in my block weights. If you are on a slower internet connection, it might take a little while to download this. I'm going to compute the interpolation. This actually, for a fairly complex process, runs pretty quickly. And then we're going to map view it to take a look at the result. And so now we have what we're doing is we're adjusting the 2011 to 2015 data to 2020 geographies. And you can kind of see how that shakes out. For example, here was my original estimate of work from home in this census tract in sort of Chandler, Arizona. It was 536. I then do block weighted allocation. Basically, the weights are based on the estimated proportion of the population in that zone. We use that as a weight. And so in this particular case, we're estimating about 97 work from home here, 95 here, 113 here, 165 here, and 63 here, which if you add that up, that'll kind of sum back more or less to the parent tract based on those weights, so long as there isn't substantial overlap with these other tracts. So this is a method that I've never written into a function before, but wanted to share with you all today. And again, this is the same method that say Esri uses to do this sort of work. So try it out, see what you think. I may put it into a package at some point. Last bit in terms of concluding thoughts, this uses population weighted interpolation, but we discussed a couple weeks ago the topic of differential privacy in the 2020 census, meaning that the block population counts may not be entirely accurate. They are noise infused. And so that may introduce some inaccuracies in this method. NHGIS, the group at University of Minnesota, doing a historical time series data set, census data. They have more sophisticated methodologies linked to that. They use land cover data as their weights. So you might consider looking at their methodology as well. And so we are now at the end, and appreciate all your time. Thank you so much for your time. And if there are a couple follow-up questions, I can maybe hang out a couple more minutes to answer those. But very much appreciate your time. And if you're creating anything interesting with these tools, if you learned anything in this set of workshops, please let me know. Send it along. I'd love to see it. Oh, last thing, of course, thank you so much to JP, to Bill, to Michael, to University of Michigan and SSDan for hosting. This is always a lot of fun.